I grew up on a farm in England, and we grew potatoes and wheat and crops like that, but we also grew tulips. Tulips are a beautiful flowering bulb, traditionally from Amsterdam, and we grew fields and fields of tulips, and I grew up amongst the tulips. It was an amazing experience. So I was born into loving plants. I love all plants. I'm especially passionate about cacti and succulents, but any plant is exciting to me. I see normally in books at home these huge trees, the climbers, the way these plants can grow so fast, the vigor, the size. Seeing unusual plants is incredible. And then I followed that all since my childhood into my career to understand the science behind it. How do plants grow? How do they react to their environment? What's the biochemistry behind that? How does it work? Without plants, we wouldn't even be here. We can't feed the planet without plants. Understanding plant biology and developing crops to feed the world is, I think, the most exciting and best thing you could do with a career. It's an amazing opportunity. I speak their language. No. As I was educated at school, I understood more. We studied wars. We studied the War of the Roses in England. We studied big events like World War I and II and genocide and the horrors that are out there. And as a child being exposed to that, it threatens your stability. It's hard to comprehend the scale and what humanity can do. And I think the many, many children growing up in war zones around the world will be, it's hard to describe how that's going to affect them. This is just such a terrible thing. And so we have to stop fighting, and I think we need to come back to nature and see how together we can understand ways that we can move forward in peace and unity and just stop this fighting. Many people perhaps have not heard of explosives as an environmental pollutant. But these are compounds that are found in nearly every country in the planet. Environmental pollutants, explosives are toxic, and they're causing damage to humans' health, and this is something we really want to clean up.
Wars don't just kill people when they happen. They leave a toxic legacy that will continue to hurt for a long time, impacting even future generations. Wars irreversibly pollute the environment, kill off entire biospheres, and render entire geographies uninhabitable for any living being. To protect the environment before, during, and after armed conflicts, the United Nations General Assembly adopted a set of 27 principles in December 2022.
The scale of the problem is enormous. We don't know necessarily where some of these pollutions are, and they quite often exist at very low levels with hotspots in unknown locations.
Several methods to remediate pollution of the soil and the environment exist. Chemical leaching is a process of using chemicals to extract contaminants from the soil. The stabilization method involves adding chemical materials to the contaminated soil to immobilize pollutants and prevent them from spreading or entering groundwater. Physical methods include excavation and removal of the contaminated soil to a safe location for treatment or disposal. The electrokinetic remediation technique uses electrical currents to remove contaminants from the soil.
So, existing traditional methods are not necessarily suitable for this. The huge area that you would have to contain and clean using perhaps dig and dump or composting, or there are techniques where you might leach the chemicals out. These can be environmentally damaging to themselves. So what we want to use is a restorative ecology. And using plants that can withstand this toxicity and detoxify, we can restore the ecology to some of these environments that are relatively barren because of the toxicity. They bring back in the microbial communities, the humic content to the soil, the birds, the butterflies, everything starts to evolve together, and we have that thing that we call restorative ecology, everything working in balance with nature, and that is the way that we can tackle this pollution on a global scale.
Offering hope is phytoremediation, which uses plants and its associated microorganisms to detoxify the environment. It's less expensive compared to traditional methods.
So phytoremediation can take up pollution, but the plants don't always have the biochemical abilities to deal with that pollution, to break it down if it's organic, or to deal with the toxicity perhaps if it's a metal. So phytotechnologies bring in new biology, new ways that we can help develop plant lines that are resistant or able to deal with this detoxification process. We can bring in genetic material, we can manipulate the plants, we can make them better able to cope, and we can harness that nature, that natural ability to help us clean up man-made problems.
Phytoremediation is an eco-friendly, organic and sustainable approach to detoxify war-affected environments.
And it was really an amazing project to be part of, and a wonderful thing to see, and it offers a lot of promise for future cleanup remediation of explosives waste.
Phytoremediation offers a number of mechanisms to remediate environmental damage. In phytoextraction, plants absorb contaminants from the soil through their roots and store them in their tissues. Some plants take up contaminants and release them in volatile form into air through the leaves in the phytovolatilization process. In phytostabilization, plants immobilize contaminants in the soil to prevent them from spreading to groundwater. In phytodegradation, plants break down organic pollutants into less harmful substances through metabolic processes. In rhizofiltration, the roots of plants filter contaminants from water to prevent them from spreading.
And that is the way that we can tackle this pollution on a global scale. The problem with these explosives, we have two main explosives. We have TNT and RDX, and together they combine and they're used in munitions around the world almost ubiquitously, and over time this pollution builds up. So we have pollution from TNT from the First and Second World War that is still present in our environment. These compounds do not readily degrade. The plants have not seen these compounds before they are made by humans, and this is the problem, that they remain and they are toxic and they're causing damage to human health and our environment. The first thing to do is to look at how plants could withstand this toxicity in their own environment. So TNT is a very, very toxic compound, and plants are not used to dealing with it because it's new to them. It's only been in the environment for maybe 80 years. So these plants, they cannot withstand the toxicity. But around the roots in the soil there are bacteria. Bacteria have very fast life cycles, as they've evolved the ability to detoxify TNT and to completely degrade RDX. So we isolated these bacteria that are around the roots of the plants on the training ranges, and we found the genes that were involved, and we transferred that genetic material from the soil into the plants that were growing in the soil. And this conferred a fantastic ability to these plants to withstand the toxicity and to mineralize or detoxify these explosive compounds. And it was really an amazing project to be part of, and a wonderful thing to see, and it offers a lot of promise for future cleanup remediation of explosives waste. I've always wanted to work in plant science since I was little. I can't remember not wanting to work in plant science. So I did my first degree and a second degree, and I moved up to Glasgow, where I was studying how plants germinate, the seed development. And then I moved down to the University of York. And while I was there, I went to a presentation by a visiting professor, Professor Neil Bruce. He has been my mentor. He's an amazing, amazing person. And he was talking about how plants can be used to remediate explosives over 2 decades ago now. And we worked together on this project for so long now. And it's been a wonderful collaboration with Neil and others. And it's been something that I'm really proud of and have enjoyed immensely.
TNT, which is used in munitions, is a toxic carcinogen that binds tightly to the soil. Another explosive, RDX, can easily leach into groundwater and contaminate the soil, resulting in serious environmental damage. Plants and microorganisms capable of detoxifying TNT from the environment have been identified.
Okay, to do phytoremediation, what we work on in the laboratory is with model plant species. We study the innate biology within these plants. We can see organic pollutants. They come into the plants, they readily cross the plant membranes and enter the plant cells. Once inside, there's an activation step. Perhaps a hydroxyl group is tagged to the compound, and then there will be a glycosylation step where a sugar molecule perhaps is then added, and then the compound will be shoved into the vacuole of the cell, if you like, the kind of safe dumping ground to keep it away from the precious biochemical machinery of the cell, so that it's stored out of the way. So then the plant will continue to grow. But if more of the toxin comes into the plant, it will try to detoxify, and after a while it becomes full. It cannot deal anymore, and you see toxicity symptoms in the plant. So what we do is we use biology to bring in the plant's own enzymes and harness those and enhance that ability by upregulating the genes or bringing in foreign genes such as genes from bacteria into the plant that enable them to do this process but more quickly, so that they can withstand much higher levels of toxicity, but also so that they can, in the best case, so they can actually break down these compounds, mineralize them. And explosive compounds contain a lot of nitrogen. So the nitrogen is quite often a limiting resource to plants. We use it as a fertilizer on our farm fields. So if plants can gain the nitrogen from those explosive compounds, then they can actually use that to grow. So you can use explosives to make fertilizers, if you like.
And some bacteria are able to break down RDX. For instance, a strain of bacteria, Rhodococcus rhodocoris strain 11Y, which was isolated from land contaminated by explosives, has been found to be highly capable of degrading RDX.
These laboratory species are really easy for the first steps, but they're not very strong or robust. On a training range, it would be a bit like driving a tank over a lettuce. It would make a good crunch, but it's not going to withstand that impact. We needed plants that were resilient to the tank traffic, plants that could literally be blown off the face of the earth, land back down and carry on growing. So we worked to develop transformation methods for native grass species, so wheatgrass species, but also switchgrass. And we could easily manipulate these plants. We know how to transfer the genes from the bacteria into the plant and how to regenerate that plant back. So that was quite an easy step in the whole process. We hit a bottleneck here. We had been working with Arabidopsis and we understood how to use it, but these new species we had never transformed before. We had to develop techniques to transfer that genetic information into the grasses using Agrobacterium tumefaciens, which is used widely, but the transformation methods we had to develop from scratch, and we also had to develop regeneration methods to go back from single cells to whole plants. And this took a lot of time and investment, and it was during this investment that completely unrelated publication came out in Switchgrass by another group working on a completely different topic, where they had developed a transformation method for switchgrass and they'd published it in open access journals, and it's a wonderful example of how we were able to use some research that other scientists had done to enable us to continue our research. And it just shows how important collaborative research is for around the world, all academics to publish in open source journals. So we were able to use their research to then develop and produce our transgenic switchgrass and wheatgrass, and we then went on to test those on the training ranges, actually growing them. And these plants, they can grow 2 or 3 meters high, so they have a massive amount of biomass, and the ability of these plants to take up and detoxify the RDX. So this technology brings lots of new hope and developments coming in. Using explosives as an exemplar, we've been able to demonstrate that this technology works in the field. We've actually done field trials, and the US military are further testing this on their training ranges, which is a fantastic thing to want to see. So I'm really delighted with that. But there are many other organic pollutants out there that we still don't know how to clean up, how to remediate. So we can use this explosives research as an exemplar to develop and transfer this technology to clean up many other pollutants that perhaps you've heard about, such as PCBs, dioxins, organopesticides, that are still out there many years after they were made. So this is a technology that offers huge promise to clean up that organic pollutant. And as we're transferring this technology into biomass crops, or big, vigorously growing species in the field, we have a lot of plant biomass coming back in, woody chips, if you like. And the plant biomass, well, we used to maybe just burn this for heat, but these days we've been more sophisticated. We are realizing that the plant biomass contains compounds much the same way as crude oil does, and by fractionating crude oil to make our lubricants and plastics and platform chemicals. So the science behind developing plants that can detoxify explosives happens in laboratories. We clone genes, we pull out bacteria from contaminated soil, we find out the biology behind that, we study the enzymes, we clone and purify them, and then we put them into the plants. So this is where we find things like the nitroreductase that can detoxify TNT, and then XBLA and B. These are the enzymes that can degrade RDX, our second explosive. And we take those genes, we study them, manipulate them, and we put them into plant model species like Arabidopsis. And then we can study the plants in the lab. These are very small, easy to grow plants, and we can do this very readily. It's common technology for plant biochemists. We can do this, we know what we're doing. But then we hit another bottleneck. We need to translate this into remediation ready plants, big, robust species that will grow out on the training range. So we come back to the laboratory again, and we work hard to develop remediation and transformation techniques, and also how we can regenerate the plants so that we have materials to take out on the training ranges and do our field trials. So for quite a few decades now, we've worked on model plant species such as Arabidopsis and tobacco. But increasingly, it's important that we translate this into crop species, and already lots and lots of research is done on rice and other crops around the world, oilseed rape, wheat, and many of the crops that are grown in large quantities. So we've developed the ability to translate our technology into there and to understand those plants a lot more. But there are still many plant species that we do not yet understand how to transform and how to bring this technology into. And a lot of them in developing countries as well. And it's important that we work more on these crop species. So the legumes, cowpeas, chickpeas, and cassava, and other crops like that, which we can develop a better understanding of these model plant, these crop plant species, so that we can use this amazing technology and unlock the potential that's out there for molecular plant science to help humanity. So challenges in plant science. One thing is funding. We need money to do this research. It's expensive. So funding from governments around the world to increase the budgets in plant science to make sure that we can work together and do what we need to do to help and produce these amazing materials that we can. The second thing that's really important is communication between laboratories around the world. And I think our communication is very good, but we also need to lift developing countries and bring in our new technologies there. So countries that have amazing genetic resources, so beautiful plant species and diversity that we can investigate. We need to bring genomics techniques, nanopore sequencing, and the ability to understand the genomes behind these amazing materials around the world in all the botanical gardens and out there in the real world. So wars happen when foolish people have power. They spread fear and hate across the planet. We've been fighting wars on this planet since we evolved, and we have learnt nothing. Still we fight. I hope that one day we will stop fighting. Clearly, I don't want to be developing technologies that clean up wars. We want to stop wars from happening. I'm hoping that we can revegetate and we can recover and we can restore, but looking forward that we can develop together and the world will become a better place. And in countries where there is equality between men and women, there is not war. I think that is the way forward.